architecture of computers itself. And we ended up talking about, unfortunately we had this ugly block there, and we ended up talking about what is an API, but also what is a system call. I just want to make sure that I got it here. So system call. This is all to do with system calls. Now, what you see on the screen is an example of a typical system call that we find in the C language, or I think it's one of the POSIX Unix Linux systems. There's a read function that will allow you to read data from a file. So you'll see that it consists of specific aspects. For instance, it has always a return type. Remember, when you had functions from your first year, it always had a return type, and in this case, it returns the size of the bytes that it read when you did the read function. It has the function name, and it has various parameters, and these parameters are dependent on the function. Now, this specific function takes in an integer type, which is, in this case, is the file descriptor. Now, understanding what a file descriptor is important. Okay? A file descriptor, whenever you open a file or create a file, it assigns a numeric value to that file. That kind of, if you want to programmatically work with that file, you actually have to use that number. That's called a file descriptor, but it's really just an integer number. So let's say, for instance, this is the first file that you open. The file descriptor may even be the value 1. But it doesn't, really honestly depends on the system itself. Then it takes in a pointer to a buffer, and that pointer to the buffer is effectively just an area where you will read, or where you will put the data into, and count is how much the maximum number of bytes to read into the buffer. Very simplistic type of API call that we typically get in a Unix environment. Now the question is, if we have this, how does the system call work? Because if you can remember from what we said last week, Wednesday, we have this border, we have these two worlds in our operating systems and our processor. They are different modes. Now, who can remember the modes? We've got hands here in front. Okay, so you remember the two modes? Can you remember the two modes? Can you remember the two modes? Can you remember the two modes? No one's two words. They are winners! Yay! User mode and kernel mode. Right, who can access code in kernel mode? Only the operating system. Whenever you develop software, you're writing and it will live in user mode. So the question now is, when you write software that does the read, you're writing that in user mode. How does the actual operating system take that instruction and execute it? That is through the system call process. Now, let's read a little bit about this implementation. So typically a number is associated with each system call. So you'll see in the next few pages, I think it's in here, that there's a number of system calls. There's like hundreds, probably not 100, but quite a number of them. Each one has a separate number. For instance, read has, let's say, number 6. Read is unique. Number 6, UR6, and those numbers are defined by the operating system developers. So when Microsoft wrote their Win32 kernel, or when the Linux developers wrote the kernel for the Linux, or when the Mac microservices architecture guys wrote their kernel for the OS X, they each one has their own set of system calls with their own unique numbers associated to it. So now, understand it. So it's got a number associated to it. The system call interfaces, it's a small little area, or it's a small little component that's built into the operating system and supported by the processor that does that translation from, that makes sure that the whole processor moves from user mode into kernel mode, but still executes the code that you want to happen. We'll show you this now. The caller, remember, is your user application in user mode. Knows nothing about the system, how the system call is implemented. It's kind of like you guys using functions in your normal day-to-day programming. In fact, it's exactly the same way. You don't care how a specific API function works. You just know when you call it, the magic happens, you get some result back. Okay, that's all you have to know. So you just need to obey the API and understand what the operating system will do as a result of the call. And most details of the OS interface are hidden from the programmer by the API, and managed by runtime support libraries, set of functions. What does that mean? It means in many cases that interface that does the switch from user mode to kernel mode happens through the library of your operating system. What is in the library of the operating system? And you can guess. What do you think is in the library? Come on, guess. There's something in user mode, eh? Something in user mode. What do you think is in the library? Is it program and system files? Not so much files. Remember which? Comments? Commands. What kind of commands? More functions. So there's a set of functions provided by the operating system, like open. Open is actually a library command that you say, listen, I want to open a file. That is part of a library inside the operating system provided by the operating system developers. You don't have to write that code. You can just go and use it. It's provided by the operating system. Typically sits there in Microsoft environments, typically stored in DLLs and all those weird things. In Linux, I believe it's stored in a .so file or something like that. I don't know, remember. But it is part of a library, and the understanding of what happens now behind the scenes of what the library does. Now, how does that library help us with the switch from user to kernel mode? So the library has the intelligence to handle that system call interface. So just remember, we said we want to go read a file. We said that each system call has a number. Now, imagine that this is one door. Whenever someone wants to come on the stage, they have to walk in through this one door. There's not more than one door. Now, in the Intel processor, there are actually, I think there are 3 doors that allows us to handle that gives us that connection. Now, just going to quickly, you don't have to know this. This is just for those that wants to learn a little bit more. In the Intel library or Intel processor, there's a number of assembly commands. You guys have done and learned a few of them already during your Thursday pracs. There's a assembly command called syscall that you can read through the details, but effectively it helps with that movement into the system. Now, basically what syscall does is it expects a number of things, and it's actually very nicely declared in this man file that's in the Linux manual. So just for interest's sake, for those that thought it's always syscall is only for x86 processors, basically the Intel processors. Other processors has other ways of doing it. So syscall is one of them. Sysenter is another way of doing it. In fact, most modern operating systems use sysenter on the Intel processor. But let's just quickly read through the syscall. Now syscall, according to the Linux manual, takes in a number of parameters or arguments, and it takes in the system call number in that register, or the one above it, or actually, this is the architecture we normally use today on our typical PCs. Now, RAX may look familiar, but you haven't really used it in your practice. You guys have used EAX. Little light goes on there, EAX. RAX is the 64-bit version of the EAX register. That's all it is. So when you see R something, it's really the 64-bit sized version of that register. So in that register, before you do the whole syscall, you load the system call that you want to run. So think of it this way. Let's assume this is the register. On this register, you load, let's say the open system call, or the open file is system call number 5. You load the number 5 on this thing, and you put it somewhere in the CPU. Now, registers can be read by anything that's currently running on that computer. It doesn't just magically disappear. Okay, so they're there, load 5 on it. What else needs to happen? Well, you also have to typically load other stuff and prepare. I mean, this, if we go back here, there was a number of parameters, remember? Like, what is the file descriptor? When must the data be stored? And what is the count? Now, what you can do, and this is how it's typically implemented in the modern operating systems, is they go to a specific area in memory and they start putting those parameters in that memory. So let's say, for instance, this is the file descriptor. Here we have a pointer to the buffer, and this is the size. These 3 chairs basically describes those 3 parameters, these 3 in front. Now, here's the read function now, part of the API. My user application called me saying, I want to go read a file. My read, when you look at the C++ code in the library, because that's what the library does, it's just a set of code, it eventually goes through that sysenter command. Meaning, I load number 5 on my iPad, I prepare these 3 chairs, and then basically I knock on the door. Okay, Mr. Colonel, I want you to do something now. As soon as you do that knock, the sysenter or the syscall assembly instruction, the guy on this side, you see I'm a different guy. This guy said, okay, the syscall wants to come in. Which one must I run? Well, let's look at the RAX register. Now you want to run number 5. Okay. Me, as the operating system developer, says whenever I go to system call number 5, which is the whole reading of files, I now start running somewhere in the memory here. There's a bunch of instructions that will execute that specific system call to open a file and go read from the platter and do something. Whenever this code starts running, it says, okay, which file must I open? Oh, I know. Part of my requirements when I do the system call, I've told the programmers that remember to put the parameters in those 3 checks. Then this guy, he can move across this boundary like nothing because he's the kernel. He can see everything in the memory. He goes to this chair and says, okay, for file number 55, that is the pointer to the buffer, and this is the number of data. Now this call instructions can execute, and it goes and it talks to the hard drive, it does whatever it needs to, it takes the data and puts it in the buffer. Let's say these chairs are the buffer, puts it in there. Also, somewhere in there it has to return the value. Now if we look at, if we go back to the command pages, the return value is also typically put in the EAX register as an example, or RAX register. So in here, we say I've read, let's say 100 bytes of data, put the value 100 in here, and then I exit. So I basically go and I open this door, and the library functions continue running. Because whenever you do a function call, you have done function calls before, eh? In your code, it gets to the function call, it does stuff, and then when it's finished doing the stuff, it resumes. So the library just resumes running, but now the data is in the buffer, the number of data that it fetches in the return type, and it then knows the data. And that's how the system call works. And that's how that interface, how that boundary is broken down between user mode and kernel. Right. So basically this is what was described. We've got here on top, we've got our user applications. They go ahead and execute certain library code, like open. It goes through the system call interface, typically implemented by the operating system library for us. It then switches into kernel mode. It goes and looks at a table. So the kernel mode, in the table there's a number of numbers, and each number corresponds to an actual system call itself, like open and read and so forth. Is it number 5? Oh, number 5 has a pointer in memory that actually has the open or the read or whatever instructions. It starts executing that instructions, get all the parameters, do whatever it needs to, and then returns. Simple as that. So what is interesting is the last instruction that your assembly, what your kernel code will execute is going to be what they call the sysexit instruction. So when we enter, we did sysenter, and then the last instruction is sysexit. That basically just switches the processor back into like user mode. Okay, right, that is basically system call. Just for you to say as well, when that processor switches from user mode to kernel mode, there's a special flag that changes its value. It's called the what? CPL, code protection level. Sorry? Okay. I think it's the CPL flag, and CPL is the code protection level, switches from 3 to 0. Remember I think one of the questions was what happened to 2 and 1. Well, they're there, but the operating system developers decided not to use it. 3 and 0 are the two code protection labels used by our modern the Intel processors. Be aware, obviously, each processor architecture has its own way of doing it, but the basic principle stays the same. So I explained that, for instance, on the Intel processor, there's certain registers that have to be prepared and so on. The ARM processor has a special interrupt that actually happens. So there's physically an interrupt that stops everything in user mode, switches into kernel mode, and there's an interrupt handler that basically then takes over. But at that point, it's effectively the same thing that happens. It looks at the register, it looks at certain areas in memory, does whatever it needs to, finishes it, and then finishes the interrupt. Okay. So how do they pass these parameters? So there's many cases more information is required than simply identifying the desired system call, so that's the parameters. Now there's 3 different ways to pass the parameter, pass these parameters to the operator. They say there's the simplest is to pass the parameters in a register. You can do that. Certain system calls just say, well, load the parameters in maybe EBX, ECX, and EBX, and that's fine. But that's honestly depends on the system call itself. The parameters can also be stored in a block or a table in memory, and the addresses of block are then passed as a parameter. This is kind of the example that we used for the whole reading thing. And the parameters is placed or pushed onto the stack. That's another option. So later on in this course, you will learn about the stacks and how that works. Typically, when you do function calls, you can do that as well. And lock and stack methods do not limit the number and length of the parameters being passed. Basically, just describes that you can have as many parameters as you like, and you can either store it somewhere in memory, or you can make it into the stack to store the parameters. Here's an example of typically where we prepare our user program. Let's say some kind of system call with the parameters for the call are stored in this area of memory. lines, they store the parameters for the call, where X is just the memory address of those parameters. And we also now do system call number 13 through whatever ways. Remember this system call number 13 gets executed. It then looks at, just an example, looks at a register that has X stored in it. So X is the address of where we could find the parameters, and then the system call goes and does whatever it needs. Right, and that's effectively how system calls work. You get different types of system calls. This is important. You guys need to know what types of things generally switches from user mode to kernel mode, and why that typically happens. So firstly, when we create processes and terminate processes, when we start an operating system and you want to start running Microsoft Word, you double click or you click on the Word icon. There's a system call that goes and creates a process for Microsoft Word. When Microsoft Word is finished executing, it then does a nice cleanup of the system that's through terminating the process. System processes can end very nicely, or for instance, it can generate errors and you will have to abort it. Both of these cases can be handled by system calls. Whenever we start processes, we must first, in many cases, first load it into memory. Once it's loaded into memory, after the process control block itself has been created, which we'll talk about later, it then can start executing them. Typically more than one system call to actually do that. Then you can have system calls to read process attributes and to set process attributes. For instance, part of the system calls are the information that we see in something like Task Manager. I'll show you what did we get in Task Manager again. All the processes that runs on your computer, I've added this process ID column, which describes each process has a unique identifier. And that kind of information, how much time is running, those type of counting information, that's part of the attributes of our process. Not just that, but some other things. And you can sometimes will have to reset some of those attributes. So, I don't know, maybe reset the CPU time, the total CPU time, and things like that. That can be done. It's done through the system call itself. We can wait for certain times to happen. So you can set certain software timers in your system, and then the wait instructions can wait for a specific time. You can wait for events, or when certain events get signaled. You can allocate and free memory as necessary. Remember, in ComSci 1 we had talked about the new and delete keyword. New is to create memory for like arrays and stuff, and delete will free that up again. You can have what they call dump memory when error occurs. So typically when an application crashes, you sometimes want to see what went wrong in your application. You can take that memory snapshot, put it somewhere, and then you can evaluate that. System calls helps with debugging of programs, and you have logs for managing access to shared data between processes. So that's typically process control. So have a look at these slides, and in the textbook they actually have categories of types of process controls. So this is system calls. These are all system calls typically we find in operating systems that focuses purely on processes. Obviously, it's not just processes that require system calls, but file management. Whenever you open a file, whenever you create a file or delete files, system calls. Opening and closing files, reading and writing files. So whenever we read, for instance, from a file, we typically specify where in the file we want to start reading. So what file, where in the file, and how much we want to read. That's reading. And you can also do what they call repositioning. So whenever we read a file, we start with, think of it as a little pointer that points to the first byte in the file. And as you start reading, that little pointer moves so that later on when you read again, it resumes where the pointer was last. but you can reposition that pointer anywhere in the file, so you can directly get access to an area in the file that you want. You can get and set certain file attributes like read only, hidden, system, and so on. There's also device management. Now what is interesting here is if you look at the device management, is there a difference between the second bullet in device management and the third bullet under file management? You see the similarity? When you read, write, and reposition the device, and read, write, and reposition a file? The answer is yes. Because when we work with typical device management, we read information from that device, we write information to that device, and the way that it can be abstracted is through the idea of a file. So you can, for instance, read information from a network interface card, as an example. And that network interface card is really just exposed to you as a developer as a file. So you open the file, you start reading data from the file. And all it really is behind the scenes, it's actually your network interface card. When you write to the network interface card data, you write information into that file, but meanwhile, it's the network interface card. So think about that, and then in Linux, you typically see this very well. There's a dev directory, DEV, and doesn't stand for developer, it stands for devices. And in that devices directory, there's like gazillions of them. There's terminal type aspect, which is basically your screen. There are disks in there, there's shared memory in there, those kind of aspects are typically in there. You can get attributes, you can set attributes, and you can attach or detach devices through system calls. There's information management or maintenance, type of system calls for getting and setting the date and time, because it changes the clock on your hardware. Okay? It gets the system gets system data, and set certain system data. It gets and sets process, file, or device attributes. Is used for communication purposes. It can create and delete a communication connection. In the next chapter, we'll talk all about messages and named pipes and remote procedure calls. And in that, we actually make connections between processes, between devices. We can send and receive messages if message passing model is used to a host name or a process name from a client to a server. Or we can use a shared memory model to create and gain access to memory regions. We can transfer status information, we can attach and detach remote devices. And the last category that we're going to talk about is for protection purposes. It controls access to resources, meaning if you open a resource, in many cases, the operating system will ensure that that resource is not allowed to be opened by something else. So you can open it for a single purpose, or basically for full purpose, you only and yourself, and no one else can access it, or you can open it in a shared way. So there's certain criteria normally per device that allows it to be shared, other times not. So typically whenever you write to a device, it needs specific lock on the device. And then obviously allow and deny user access. This is just a few examples of a few system calls and how they differ between Linux and Windows. So on the right hand side is your typical Unix Linux environment, or POSIX is another word for it. And here in the middle is our Windows system calls. And if you don't really do C++ programming, the chances that you will ever use these types of system calls directly are very, very slim. But this is kind of what happens behind the scenes whenever you use a high-level programming language like Java or C# or those kind of things. That all get translated eventually into the Windows library, which is really just C++ code to create processes and set things and read things and so forth. Right, the standard C library example. So the standard C library is a library. This is what I've tried to explain when I ran up there, asking what is a library. It really just explains how certain system call translation is abstracted away from us as the user, and the standard C library does that job for us. Most operating system, or the C language, is one of the basic programming languages that we use to develop operating systems, and that's typically one of the first things that gets compiled for that architecture, so that you can build your operating system on top. That's the role of the standard C library. Okay, the next few slides really just explains the nature and the differences between single tasking versus multitasking operating systems. Please go through in the textbook the following aspects of your system calls. There's no real that many details around it. Basically, in 2.4.2, well, basically the 2.4 section in your textbook, please just go through that in a little bit more detail. It talks about file management, file system management, device management, information maintenance, communication protection. Basically, these things that we went through, but just go through the details of it and get a better understanding of why you would use one type of system call versus another type of system call. And then the last thing when we talk about system calls is really just a quick example of the different types of operating systems and how typically system calls affects the architecture of these operating systems. Now the first one is you can look at MS-DOS. Now it's a little bit of a misnomer to say that MS-DOS had system calls, because there was no user mode and kernel mode in MS-DOS. It ran what they call real mode of the processor, and the processor had only 1 megabyte of memory that it could access, and everything ran in this 1 megabyte of memory. It could only run one application. When the system was booted, the shell basically started, which was the MS-DOS shell. And then when you ran an application, you had to basically type the application name. There was no process that was created. Basically, the command interpreter actually loaded the process over a component of the command interpreter. So you see on the left-hand side, it shows the command interpreter taking up a certain number of area in memory. And when the command interpreter started that application, that process actually overwrote the component of the command interpreter so that it could use up as much memory as possible. You didn't need to have the rest of the command interpreter loaded into memory. When the process finally finished, you basically had to restart your computer and MS-DOS again started. Or if you could break out of it, the command interpreter must basically then be reloaded into the memory of the computer. So when the program exited, the shell was reloaded. Something like FreeBSD, as an example, is Unix variant. It's a multitasking operating system, which basically means that the command interpreter, which is this thing here in blue, never gets unloaded in memory, because when the command interpreter starts a process, it can start the process somewhere in memory, or through the kernel does a system call, it starts the process itself, and it stays in memory, so that you can start the second process or a third process. And each of these processes effectively runs somewhere in the memory of your computer. So there's a few examples here that just describe the fork system call. Basically creates a new process, and then exec basically loaded that program into the process, and then the shell would then wait for the process to terminate or continue with some user commands. Either choice. You could have either interactive still in the back end, or you could basically wait until the process exits. Alright, there are a certain number of programs that ships with the operating system that helps us with the operating system. These are typically what we call system programs. In Windows, for instance, the File Explorer is one of the programs that helps with file manipulation, moving files, and so forth. But effectively, these system programs does certain things, and you typically have system programs, or system programs helps with file manipulation, status information, programming language support, communication, background services, application programming, and so on. I'll just quickly go through this. This is not that important. You guys can read through this a little bit later. So there are a number of system programs that help you in your typical operating systems, and each operating system obviously has their own versions of these system programs. Alright, this brings us to the next important section in this chapter, which is operating system design and implementation. So why do we do this? Why is it important for you to know how operating systems are designed? Well, when we work with operating systems, sometimes you are going to write, for instance, let me give you an example. I have a friend that works for the company name now, but what they effectively do is they help write the switching systems that takes the SMS messages and messages on the Vodacom network. For instance, that helps implement the whole, let's say, please call me architecture behind the scenes to handle all of those messages. They write this system in the C language or the C++ language so that you get speed, because they handle like millions and millions of these messages per minute on that system, and they need the speed. So that whenever you're going to want to get speed, you are going to write C or C++ programs. That's just the reality. The reason is that compilers compile very close and very efficient assembly language versions of it. Where if you're going to write in a higher level language such as the .NET framework or Java or even JavaScript, very far removed, it basically has to go through a number of layers of implementation before it actually gets to the assembly instructions. Okay, now whenever you get to these assembly or C programming languages, you are going to sometimes need to parse and create certain structures in your operating system or a system so that you can exchange data very quickly. And this is how what we're going to talk about here is it helps to give you an understanding of why sometimes certain things are slower, why sometimes certain things are faster, but it also explains why certain operating systems can use the following mechanisms to exchange information and why other operating systems cannot use those mechanisms. Okay, so this, together with the next chapter, will explain those mechanisms. Alright, let's quickly, for those that want to leave, get our meeting. Yes, we will continue with the next office. So last week we had a student that an hour after the class attendance was actually taken, there was something came in. I think it was weird, wasn't in the class, wasn't in the cellular networks in South Africa at least, so someone had to share. So yeah, you see these things. still busy? No one? There's someone still busy. Wait for a second more. Imagine if you're writing a test and I ask a question such as, imagine you're going to develop an operating system and you need to design a system call interface. The following are a few requirements that you must make sure. Please explain how you implement such a system call. I can give you the requirements such as the parameters must support multiple parameters, one, and there must be multiple system calls in the system. Please explain how you implement such a system. Okay. Nice 10, 13 mark question. May I repeat that? Basically what I've done is by running up around, walking on the door, explaining things like that. Okay, you still busy?
Wait, so the question like that, do we have to go into like
Good question. So the question is, do you have to go into really a lot of specifics? The question is asked, how would you implement such a system? Then you will describe the typical components that you will have in there. For instance, you will have a list somewhere in kernel that, for instance, has the number of each system call will be listed in that list. Each one with a pointer to an area in memory that will have its own unique code. You will then explain that you will have another structure where you will pass the system call number into. This can be a register or whatever. You can decide whether you want to make use of a memory location for your parameters or you want to use the stack. Your decision. Then you explain how that process will go. Like all people ask you, explain then how this type of system call will be implemented. I make use of like file footprint, something weird. Next. Okay, let's have a look at the design. What is interesting is that if there's a golden way of creating an operating system, if there's only one way to create an operating system, then why hasn't everyone that developed operating system done it that specific way? And the answer is that there is no one correct way to design an operating system. There are different ways to do it, simply because there's different objectives that we have in operating systems. And some people claim that it's more of an art form than it is a science. And that, I think, is kind of true for many types of programming problems that you have in the world. I think who doesn't have informatics 3 as a subject? So there's a few. You guys are the clever ones, because you don't have to do a project. So what subject do you have instead of applied maths? Okay, is that more clever? I don't know. I was one of those students that was really scared of an informatics 3 project. But for those students that do informatics 3 projects, you should know by now that there's no one way to design a solution. In fact, you guys this year are going to use one thing, and next year you're going to work for internet or discovery or for whatever, and you're going to say, really, did we program that thing? There's different ways of doing things. There's no right or wrong way of doing it. But it's kind of like the more you do it, the more you come to the front as an artist of a way to do things nicely, it looks cool, and you kind of formulate your own way of doing things at the end of the day. And that's kind of the same with operating systems. So the first thing when we look at the goals or the designs of an operating system. We have to understand the goal and the specifications. Why are we writing this operating system? And be affected by the choice of the hardware, the type of system, obviously, because if your processors can only do this type of thing and doesn't support that type of feature, then you can't build that into your design of your operating system. There's also a difference between user goals and system goals. Users want something totally normally different from system goals, like typically your user goals, the operating system should be convenient to use, easy, should be easy to learn, reliable, safe and fast. But some operating systems doesn't need users to work with it every day. If you look at the operating system that runs your engine management system in your car, as an example, you don't go and type in dir, start motor, now, start. You don't do that, yeah? You either press a button or you turn the key and then it starts. And those things happen behind the scenes. So it honestly is dependent on the type of operating system we have, the architecture behind it. But there's also system goals. Certain types of systems work differently for different purposes. Operators should be easy to design, implement, maintain, as well as flexible, reliable, error-free, and efficient. Most of the time, those goals are kind of stock standard. I just want to warn students that like to write complex code. Don't write complex code, please. It's difficult to make. Rather make code easy to read, even though it's sometimes 1 or 2 lines extra. It's sometimes easier to understand than really complicated pieces of code that only spans 3 lines. If you're ever interested in interesting algorithms, what was that game? There was a game, one of the first-person shooters that came out, there was a problem that they had where they had to go change the algorithm behind it. I'll see if I can get it and mention it to you guys. And then this person, really like a genius, there was a lot of floating point calculations that happened in that game, and the way that it rendered the first-person environment really made the algorithm so short, but it's so unintuitive. You don't understand what the hell is happening there. But everybody is basically adopting that algorithm in their first-person shooter games simply because it's the most efficient way of doing it. But very few people can actually describe what's happening in there. Yes.
Are you referring to Quake?
Yes, Quake. Yeah, it's in Quake, and I can't remember what that algorithm was. It is fascinating. Obviously, if you understand the maths behind it, it's really cool. But I don't. I didn't even have applied maths. Right. I had geography, and I know. Computer science and geography. Not all. Right, guys, let's go on. So there are a number of principles to separate. This is important. Policy versus mechanism. This is something that you can adopt not only in operating systems, but any system. So there's a difference between things that you can configure and the way that you implement. So the mechanism is, how do we do something? So how do you, for instance, read a file from a hard disk? The policy is, what will be done? I need to read a file, I need to read X amount of data from a file. Those things you can set separately. So the principle of policy and mechanism is always important to try and separate in your systems, so that your policy typically changes over time, but your mechanisms typically stays stable. There must be a way in which you can interface this. So mechanisms determine how to do something, policy decide what will be done. Separation of policy from mechanism is an important principle. It allows maximum flexibility if policy decisions are to be changed later. For instance, something like the timer they mentioned. Specifying and designing an operating system is a highly creative task of software engineers. So the reason why they talk about a timer there is just that you can have different ways to implement a timer, but exactly how quick the timer should time, or those things you can actually, if you can keep that separate, it makes things easier. So I want to be able to measure once every so many milliseconds, or once X amount of time per second, or something like that. That's policy. Implementation. how do we implement operating systems? Just make sure I have everything here. Okay. There are many ways to implement operating systems. Early operating systems were written purely in assembly language. Horrible. But they weren't that big. Then systems programming language like Elgol and PL1 was developed to actually help with operating system development. And then later on, probably when the C language was first developed, it was a real breakthrough because that was the high-level programming language that most developers use to actually develop the operating system in. These days, we kind of have a mixture. We don't just develop operating system in pure C or even C++. We have probably 99.999% of the code is written in C or C++. However, there are certain components. Specifically, you will learn the interrupt handlers, which is the things that knows when an interrupt comes in, it has to do certain things so that it can save the state of the previous process, start the next process. Those things must run very, very quickly, and that is done in assembly. Now, the reason why we don't just program in assembly anymore, I think, are two reasons. The first is you can make this very easy to make a mistake in assembly. I mean, you should know that it's not the most intuitive programming language there are. Plus, our compilers these days they are brilliant. They can develop they can compile a C or a C++ application into an assembly version, probably more efficient than user person can do. Well, as a third year student, definitely. As a lecturer that's been giving this course for a number of years, I typically add, on average, probably 10 to 20% more code than what an assembler will do. It's just compilers. Compilers are extremely efficient in the way that they can actually create the code for you, if it was done in the C and the C++ language. Obviously, .NET frameworks and those interpretive languages are a lot more inefficient with regards to the way that it gets executed. So just be aware of that. So if you're going to ever want to go write your own device drivers, I don't know if you're going to want to, it will probably be happening in C++. Obviously, a big advantage of writing an operating system in higher level languages like C or C++, it's very easy to port it to a new piece of architecture. So that's what makes Linux so nuts. The source code of Linux is very easy to port from an ARM processor into an x86 processor, into a PowerPC processor, into a RISC-V processor, or whatever. All of these architectures are different, but you potentially have different header files that will just explain things a little bit differently from the architectures, and each one will have its own C compiler that will know how to translate that C code into the assembly language. Emulation can allow operators to run on non-native hardware. So what happens, we've already talked about this, but effectively, you get a number of emulators. Box is one of them, QEMU is another one of them. You can actually install these emulators on your Windows machines, etc., etc. Now, what these emulators do is they translate assembled assembly code into a different architecture. So whenever an assembly instruction runs, for instance, for an ARM processor, an emulator translates that assembly instruction into an x86 instruction. That's what emulators do. Different level of abstraction. Above that, obviously, we've got virtual machines, but in those cases, it must the compiled applications must be for that architecture. One level above that is your containers. Have you heard of containers?
So what's the difference between emulation and interpretation?
Emulation and interpretation. The question is, what's the difference between emulation and interpretation? What you typically can think of as interpretive languages is Interpretive languages are things like the .NET framework or Java. They run inside some kind of runtime environment. So it's a very, very high level language. It then gets interpreted into the architecture that it has to run on top of, and then it gets executed. That's that's what interpretation basically means. Emulation is the actual assembly instructions gets translated into another assembly instruction. So interpretive languages are very, very high level. They always have to go through this interpretation process from, let's say, Java, what is it, run code, I think it's called, or I can't remember. What was it? JRE. Well, JRE is the runtime environment, but I think there's actually a name for it.
Bytecode.
Bytecode, thank you. Bytecode, it basically gets always compiled into bytecode, and then from there it gets translated into the assembly by the runtime environment.
So my question is, why would a program written in assembly be faster than one written in C? Isn't C compiled down to give us like executable machine code by the time it's done?
Yeah, so the question is, why will assembly typically be faster than, for instance, an assembled C or C++ program? And in general, it may not be, but those small pieces of code, as I've mentioned, that typically handles your interrupt handlers, they are written by people because there's a lot of hardware involved in those cases. And that's the only thing that from what I've read, is that's the reason, because it needs a special interpretation of how the hardware works. But I cannot comment because I have never ever written my own interrupt handler. Well, fortunately. Okay guys, that's it for today. You can go now. So